So, everything we've been looking at in this entire course has been mechanizing pure logic of some sort. Actually, going back to the early 20th century, people like Russell were arguing about questions like, could mathematics be reduced to logic? Which is kind of a funny question, because you have to answer things like, what is mathematics exactly, and what is logic exactly? And these kind of definitional things, you fall down a rabbit hole very quickly. So the thing is, though, in real life, sometimes you have to prove things with numbers in them. Now, actually, I don't know why I chose this particular example. This is kind of dumb, because, well, this is a very mathematical example because it has pi. But if you're verifying a program, you're much more likely to have some kind of expression on which the correctness of your program depends, which probably won't have pi there, but it will have a lot of numbers, and you need to know that, for example, the thing that you're using to index a block of memory really lies within the bounds, and so on. Looking at the technology we've surveyed so far, we have seen nothing that can deal with numerical problems. Actually, we can deal with numbers in pure logic. So if you've maybe heard, I have my own interactive theorem prover called Isabelle, in which one can represent signed integers using a kind of almost binary representation, symbolic. I mean, this is symbolic binary, so not the bits in hardware, but a syntactic expression which is effectively binary, and with that you can get a reasonable representation of even very large integers. And then, of course, pairs of them can be rational numbers. And yeah, you can do some of this. This is not always the best way, certainly if you're trying to do some kind of static, kind of logic-based checks on 2 million lines of C, that's not the way to do it. So let's look at the broader question of somehow integrating other stuff into our logic. So this arose originally, I guess people were doing this in the 70s. They wanted to verify programs, and these programs contained integers and reals. They contained something lists or other data structures. Of course, they had truth values and arrays, and as well as pure logical reasoning. And so a lot of work was done on what was called combinations of theories. So one particular thing that emerged was the notion of a decision procedure. I should mention this whole lecture is kind of a big aside, though it is an examinable aside, because we are going to go back to pure logic. Nevertheless, I want you to have a glimpse of this. It's an important part of computational logic. So you are studying computation theory at the moment, and the notion of decision problem comes from there. A decision problem is any sort of reasonably rigorous question for which we can write a computable function that says yes or no. So like the question, is a number prime? I can write a computable function. You give it its input, and it will terminate in finite time, always. It will always terminate, and it will give a yes or no answer, and that will be correct. That's what a decision, well, the decision problem is, can you write such a program? And you have a decision procedure, if indeed it is such a program. So lots of decision problems are, in fact, not solvable, like the halting problem. You know that's undecidable. And many other things turn out to be decidable but hard. So you've probably heard, although you don't get it till next term, the satisfiability problem for propositional logic, that is the exact problem solved by SAT solvers, is a so-called NP-complete problem. That means it's likely to take exponential time, and various other things are completely undecidable. In fact, almost even the things that we can do turn out to be pretty damn hard. That's unfair. Nevertheless, there are lots of things we can do, and decision procedures help us a lot. Before I go back to my slide, this course is entirely about automatic theorem proving. So everything we look at is okay, you're doing it by hand because you have exams, and also you need to learn how these procedures work. But very few people in their right mind are going to do sequent proofs, after they leave the course. They're certainly not going to do resolution or SAT proofs after they finish the course. You might write code to do these things. So they are, and this code you write will be for a completely automatic thing that proves theorems. There is a whole other branch of so-called interactive theorem proving, where people are kind of interacting, as the name implies, with a system that knows logic, has proof procedures in it, but also can be guided by the human being to say, like, here's what we're proving, I need to do this, and it will kind of interact with you, and that's kind of cool. But it can be extremely tiresome to prove even the simplest thing. This is a problem we are beating our heads against the wall over and over again, trying to prove things that are obvious, and somehow making it rigorous turns out to be extremely lengthy and tedious. So decision procedures originally became popular because they could solve a lot of these problems very easily. Now I have a few examples that I will go through as the kind of things we can decide. First of all, and going back to the world of pure logic, we now have very powerful decision procedures like DPLL, where you can, I think I mentioned this book by Lewis Carroll from the 19th century with logic problems that might have seemed awfully hard by the standards of the time. Or indeed, if you open a newspaper and you find a Sudoku in there, a Sudoku is a pure logic problem. In fact, you can very easily translate a Sudoku into propositional logic. It will take you all day to do a Sudoku, probably, but they are trivial. So if you encode it in the right way and give it to DPLL, it will be solved in milliseconds. So it is, in fact, a trivial problem. And so these decision procedures save us a lot of work already. The other thing which helps us a lot is so-called linear arithmetic. What we mean by linear arithmetic is we are banning multiplication and division. Or to be more precise, we have the relations, we have addition and subtraction. If you do multiply and divide, you can only divide or multiply by a constant. Now, I think this first attracted people's attention. Well, firstly, people who knew their logic, they'd maybe done a course at university and learned about a thing called Pressburger arithmetic, which is exactly this. Linear arithmetic, even with quantifiers, turned out it's decidable. And then they noticed that if you're trying to verify, let's say, some simple code to do something with an array, so back then it was Pascal, you'd have, verifying a program then meant you had, 3 dozen lines. You would look at what was involved for that to be correct, and you would get a whole bunch of expressions like this that would show you maybe that the array was accessed correctly or whatever. And these sorts of things, if they were just spewed out by your verifier and said, you've got to check these, they were not very easy for a human being to check. So it was really cool that you could write some code that could check them. So like this first example here, maybe I didn't sleep well, but I can't see immediately that this is satisfiable. Luckily, I put the answer right on the slide. You can work out the numbers for yourself. Equally, that this is unsatisfiable is not obvious to me, and then it's also harder for you to work it out for yourself, but if you want, you're welcome to try it. And it turns out in the real case, you could even do it with full multiplication and division, but it gets way harder. I probably mentioned already that the problem with real numbers, even with multiplication and division and quantifiers, is still decidable. And that means, in fact, you can encode Euclidean geometry in this language and now have an algorithm to solve any question in Euclidean geometry. So Euclidean geometry is actually a decidable branch of mathematics. Fortunately for the jobs of mathematicians, most of mathematics is undecidable, and even for Euclidean geometry, you get a tower of exponentials when you try to do this, so even it is not feasibly solved in that way. Now, I'm going to give you a taste of how such a thing can work. Well, you've seen one decision procedure already, which is DPLL. In fact, you've seen two because I showed you how you can convert formulas into conjunctive normal form and decide whether they're tautologies or not. But we'll look at yet another. This is for real linear arithmetic. And despite the somewhat scary looking everything, it's almost trivial. First of all, this is 19th century stuff, right? And you all went to school and you all learned how to solve systems of simultaneous linear equations, right? You know, you have your equations, you multiply one equation by another and subtract it, and you eliminate variables, and you keep eliminating them until finally, you know, x equals 2 and y equals minus 3 and z equals, you know, you can do that. It's almost exactly the same algorithm here. So this is a naive algorithm. Nevertheless, it can already do some impressive things. So what I have written here, this first thing is the conjunction. That big, funny-looking thing is simply the conjunction symbol. We are anding together m formulas, and those formulas are simply the sum of various terms where the a's and the b's are, let's say, real constants, and the x's are the variables. So these are just very simple constraints in which we have some number times x less than or equal some other number. So we are going to try and decide these conjunctions of inequalities. Now, to keep it super simple, I'm only allowing less than or equal here. And the idea, just as I said, with a system of linear equations, you can subtract the one from another and eliminate the variables. That's exactly how this one is going to work. I said it all. This is not very efficient. So if you can read that, this is a hyper-exponential algorithm. Now, you were told last year, I think, that an exponential algorithm is already not worth trying. So why would you even dream of trying this? Well, it turns out it often does give us a good result, and there doesn't seem to be anything better. Now, actually, I don't know. So I'm quite honest to tell you, I do not know whether there is a sub-exponential algorithm for solving such systems. It's an interesting question. I mean, if you had such a thing, could you use it to do could you use it to do propositional satisfiability in less than exponential time, you know? But I mean, that is hyper-exponential. It would be nice to have a decision procedure which is no worse than exponential, but I don't know if such a thing exists. Anyway, let me go through. I will work through this even with an example. But I'm giving this to you in an algorithmic form, even though, as I said, it is almost exactly what you already did in school with systems of simultaneous equations. So we eliminate our variables one after another until every variable has been eliminated. And at that point, either we have deleted all the constraints, which means satisfiable, or we've arrived at a contradiction, at which point we immediately stop and the whole system is unsatisfiable. So the idea is to rewrite these things. So we rewrite every constraint in this form. See, the idea here is to isolate variable xn. So xn, I guess, is the last variable. I think when I do this informally, I'm going to do it in the way that gives me the shortest proof because I'm lazy. But if you're doing it as an algorithm, maybe you'll do it in a completely deterministic way. So if you want to eliminate the last variable, you take all the other variables You can define these things in terms of them, and then we rewrite the last constraint so that now xn has been isolated, right? So we've divided it by its coefficient, and this beta represents all the other variables. And the reason I have to have the greater than 0 case and the less than 0 case separately is because, as you know, if you divide an inequality by a number, you will flip the inequality around if that number is negative. So we now have, so each of the m constraints we had can be seen as constraining or involving all of the variables, unless, of course, the coefficient of that variable is 0. And so we will rewrite them in this form or that form. Now, if you add these together, the xn's will cancel out, which is the whole point. And now we have a constraint in n minus 1 variables. Do every combination of this, and we have, we certainly eliminated xn. There is some theorem or other, which is not very complicated, that proves that, well, this is clearly a sensible thing to do, then, that everything that we are doing here is logically correct. What you want to be assured of is that you're not going to lose any solutions by doing this. And I think there is some relatively simple proof that if a suitable value of xn exists, then the corresponding reduced system will also be satisfiable. So you keep doing this, delete the original constraint that had xn in it, and you have eliminated xn. Keep going until you cannot continue any longer. And I know that didn't make any sense, so here's an example. This is a very simple example, and as I said, these things originally started to come from attempts at verifying code. And if you looked at actual code in which you are addressing memory buffers or whatever, you know that the combinations of things here can get pretty complicated. And ideally, you know, if you've got thousands and thousands of these problems to be checked, they've got to be done automatically. So what's going to happen here? I have kind of worked it out already, and I don't feel clever enough to do it by myself. So, but I think the thing that you could obviously do, now this is not doing the algorithm. Remember the algorithm, I carefully numbered them from 1 up to n and said eliminate xn first and all of that. But I would be tempted, just looking at this and being kind of dumb here, is to say, why don't I eliminate the x's by adding those two and adding those two? The x's will cancel out. And is that what I did here? Yes, it is. That's very nice. So when I added, which was it? How did I get z less than or equal to 0? If you add those two, okay, first of all, the x's cancel out. Secondly, the y's are on opposite sides, so they will also cancel out. So you get 2z less than or equal to 0, which is z less than or equal to 0. I understand what I am doing in front of you is not very algorithmic, but it can be put on a rigorous basis. What about this one? You add them, the x's cancel out, the z's there are on the opposite side, so yeah, you get y plus z less than or equal to 0, and the last one you just carry along. Now, I guess the obvious thing to do is eliminate the z's from this, because you can add those two, and you can add those two, and I think I know what's going to happen, because that will be 0, and that would be minus 1. Yeah, you've got 0 less than or equal to minus 1, which is simply not true. Okay? And what I just said verbally is on this slide here, which is in your notes if you don't believe me. And now, this is one of the better ones. Yes, you don't want to mess with that lady. Okay. Now I'm going to drift on to an even more remote tangent. This is rather advanced stuff that maybe you will not come across again, but it's cool. So it does you no harm to see it for 5 minutes. What is quantifier elimination? Well, it does what it says on the tin. It eliminates quantifiers. Now, actually, a lot of things we've seen already are concerned with getting rid of quantifiers. So Skolemization, when we skolemize clauses, we get rid of the existential quantifiers, and then because everything at that point is universal, we can throw away the universal quantifiers as well. Remember then the thing we then get, we kind of interpret as universally quantified anyway. Here, quantifier elimination is something much more powerful because instead of merely preserving satisfiability, this time we preserve the exact meaning of the formula. So this can do some really cool things. So the idea here, I'm sorry to keep this, again, a very low budget PowerPoint to put pieces of paper on top of other things. But when you have your constraints, and this is a really, really simple of constraints, right? 2x less than y less than x. What does it mean to have this as a system of constraints? What it really means, I'm asking, do there exist x and y to make this true? So this system of constraints we're really viewing as an existentially quantified formula. Now, this particular formula has no free variables, right? Remember what a free variable is? X and y are both bound, and there are no other variables. Quantifier elimination will replace it by an equivalent quantifier-free formula. And that formula can only be true or false, because if there's anything else in it, it will have free variables. True or false are the only possibilities, and in fact, as we simplify it here, we have eliminated first the inner quantifier. I see, somehow we simplified it to that, and that in turn we can eliminate this quantifier, and it's simply true. And if it were unsatisfiable, it would be replaced by false. Well, that is going to give you an over-optimistic picture of things because, yes, if you have quantifier elimination on any formula without free variables, your result is guaranteed to be true or false. So that's a decision procedure. You may unfortunately have to wait a while to get there. And if the formula does have free variables, you can expect a tower of exponential. Sorry, they keep coming up. And even when you are replacing it simply by true or false, so the answer is very small, the time taken might still be hyperexponential. And if there are free variables, then the length of the formula might also be hyperexponential. So maybe I shouldn't quite be talking about this here because you're normally, as a computer scientist, not going to implement anything that needs hyperexponential space, for heaven's sake. Although I would just say I did an awful lot of programming on a 16K computer well before you were born, and we did useful things. Right. This is one of my favorite examples. No doubt you have seen something like this long ago in school, right? You know what that is? Solving this quadratic equation, or this is actually a slightly different question. There's simply the question of, does this quadratic equation have a solution? The thing is, there is software that can actually convert that into that automatically. I think, to be honest with you, I may have tidied it slightly because I may have presented it in a slightly uglier manner. but this is in fact the exact necessary and sufficient conditions for the quadratic equation to have a solution, which includes, by the way, why is A non-zero there? So if A is 0, it's not a quadratic equation at all. So we have, you can check not only the obvious thing you expect, which is this, but why it has these other things as well. Okay, so this, and again, this shows you the power of quantifier elimination when it gives you a nice simple solution, although, as I say, in general, you probably don't want to look at the result. So what else have we got here? These are just names of things, right? You don't have to learn these. But, wow. So it says on my own slide that all decision procedures for arithmetic seem to have a hyperexponential complexity. I must have looked that up somewhere and forgotten it. That's a rather depressing fact. So people go to all this trouble to make these fancy algorithms, and they're still hyperexponential, right? And you complain because your sorting function is quadratic. Okay. Now, there has been a lot of research, mostly in the USA, and in fact, when they say theorem prover, they're generally talking about a different thing. So when I say theorem prover, generally I'm thinking resolution, actually. Generally, in America, they usually resolution is no good. And they are looking at, first of all, things that can combine lots of decision procedures and also are using the thing I am about to show you. But before I show you that, well, that always works. Okay. So we are going to have a glimpse at a thing called SMT solving. This always worries me a bit because, well, the scope for confusion is very high, but this is a very powerful technology that you need to know about. The reason we need, well, the thing is, if you have the decision procedures I just showed you, they are very clunky to use in connection with normal logical formulas because they only, all the familiar ones want to be given conjunctions. And the fact is the world does not consist of conjunctions. And that means you have to use disjunctive normal form because then you are ORing together a bunch of conjunctions when you somehow have to feed your conjunctions into this thing. And that is not going to work very well when especially all our other technology is based on conjunctive normal form and so on. The whole thing is no good. So somewhere around 20 or so years ago, SAT solving had really taken off and was doing amazing things, and some smart guy thought, can we somehow hook this into DPLL? That is, somehow make a connection between decision procedures and DPLL. And they came up with a general way that you can connect basically any well-behaved decision procedure for almost anything with DPLL, and what that gives you. So when they say modulo here, they're saying it's doing Boolean satisfiability, but it also is understanding some theory for which you have a decision procedure. That means in particular that the part of the reasoning which does not involve the decision procedure, which is pure logic, is going through DPLL, which is a pretty powerful, effective tool. So the idea, and this is where the confusion leaps in, and I think there'll be some of you who in the heat of an exam will forget what's going on here. So let me just shout it out. DPLL only works for propositional letters. What we're going to do here, when we do SMT, we're going to do a really weird thing. We are going to start having propositional letters with names like that. Why would anyone do such a crazy thing? It's like doing group theory and saying, let's let 3 be a group. Nobody does that, right? Because 3 means something already. So why would we make a propositional letter have a name like that? Well, because we are going to be doing 2 things. We're going to be using DPLL with propositional letters. And we're going to get models out. Because remember, DPLL finds model, that is, it finds satisfying assignments of the letters. And then we're going to take these letters and say, okay, Mr. Decision Procedure, according to DPLL, 2x can be less than y. And the decision procedure is going to see this as an arithmetic formula. But DPLL sees it simply as a letter. Again, the reason people get confused, so I sometimes see students thinking, you can have variables in StatSolver, which you cannot actually do. Anyway, so the cool thing is this. So you put in your clauses, which have these weird-looking letters, you run DPLL, and if it has a contradiction, that means that even from a purely logical basis, the thing you gave it is unsatisfiable. Okay, you're finished. It's unsatisfiable. But if it gets a model, then you take those weird-looking letters, you give them to your decision procedure, and say, what do you think? The decision procedure, if it says unsatisfiable, then the decision procedure will say, you didn't find a model, you thought it was a model, but when I interpret your 2x less than y and whatever else together with it, that actually is not a model at all. That then is fed back to DPL and says, I got to search again. So in this way, every claimed model is then checked with this separate solver, and then if the solver says, it's satisfiable, then you're finished, right? You've satisfied your clauses even to the level of the decidable theory. But if it does not approve of that conjunction, you have to go and run DPLL some more. Now this is a very, very general thing. Now I'm showing it for linear arithmetic because that is the simplest thing I can think of. But you could have absolutely anything in these letters, provided you have a decision procedure for that thing. So this, and remember, each of these things is nothing but a propositional letter. So we are going to run DPLL on this as usual, and for DPLL, with the one exception, can you accept that when I write C not equals 0 here, I mean not sign of C equals 0? So, sorry, I was almost going to do resolution. Let's do DPLL. We have a unit clause, so we're going to presumably do unit propagation here. That will go away, and that will go away. And so we have these clauses left. Another unit clause there, so C equals 0 is false. That will go away. That will go away. So we deleted that literal. We're left with this, and we're left with that. And now what? We have another, probably a pure literal at this stage. Well, I could have called it a pure literal as well. Here I'm calling it a unit clause. It didn't make any difference. I can even, shall I switch this on? Is it worth it? Is it worth trying to use the other one? Woohoo. Okay. So we ran DPLL, treating these things, each of these weird things, as a propositional letter, and we got a model in which we said, well, B is less than A, C is non-zero, 2A is less than B. And then we thought, okay, everything is true. Wait. We're not quite finished here, so we are continuing with this, and we say, okay, let's do a K-split on this last letter there and say we have a model. And now we feed those four things which we had been viewing as propositional letters, but now we give them to a linear arithmetic decision procedure, and it says it's going to view them as arithmetic, and it will say no. And it can do more than that. There is a clever thing they do if you want this to work properly. What you do is you modify your decision procedure so it can tell you what they call the minimum contradictory set. Or they call it, I think, an unsat core, which is awful bit of jargon. The point is, if it's not possible for all of these to be true, that means one of them must be false. And so you can turn that into a clause. One of them must be false. That is an actual mathematical fact. We can actually plug this back in as a new clause and add it to our existing clauses. And I think 1, 2, 3, 4, did only 3 here. So it looks like the non-zero C had no role to play in the contradiction here, so it was actually dropped by the decision procedure. The decision procedure tells us these 3, one of these must be false. They cannot all be true. This is a new clause added to the set of other clauses, and then DPLL continues. So eventually it appears the SMT will terminate with a genuine model which looks like this. So I hope it's clear, this is a cool capability to have. So the full logic and performance of DPLL plus the ability to include arithmetic or other specific theories that you know how to decide. And so certainly, especially American researchers, when they talk about a theorem prover, they're talking about a thing that does this. Probably the best known of these is a thing called Z3, which is made by a very obscure software house called Microsoft. And you can download it from there. And now I just want to mention, because it makes my heart break on exams when I see people looking at a formula where they should be using resolution and they're deciding to use DPLL instead because they remember that DPLL can have a little constants in them. So please don't get confused. I'm just telling you once again, these for DPLL, these are, each is an atomic variable and not an expression. Okay. But the cooperation between two reasoners, this is actually a big thing now in the automated reasoning world, to have lots of specialist provers, each of which is very good at one thing. Okay, so just to finish up, I mentioned Z3. There are a couple of others. As I said, you can try downloading. Any of you tried downloading any of these things yet? I mentioned last week. Go on, waste some disk space on your laptop. A lot of these things come with big example files and might blow you away just looking at, if you are annoyed by the exam questions you see, wait till you see one of these input files. These things are being used a lot now. All the big companies that you've heard of are using this sort of technology. Amazon Web Services, Microsoft, Apple, NVIDIA, and so on are using this sort of thing. I'm not sure I want to list every one of these, but we are at the point where you can feed large amounts of source code into an automatic tool, and it can do loads of very sophisticated program analysis. Now, we're not at this stage talking about full program verification, so we do not have any means of fully automatically verifying program code. But we can do now very sophisticated checks on arbitrary, even code written in C. So we have really moved a long way, certainly since I've been working here. Okay, and that's it for today, so thank you.